Hey physics people. So here is an explanation of these first set of notes for you. Okay? So electric fields and potential. So every space around an electric charge has an electric field. Okay? So it's a field surrounds that charge or a group of charges. And basically it holds an electron around a proton, kind of like a satellite is held around Earth. Okay? Gravitational field, electrical field, kind of work the same. It has magnitude and direction, so that means that it's got a strength, its magnitude, and it's obviously going somewhere. And so you can measure its strength by its effect on the charges that are in the field, that are located in the field. So the direction of the field at any point is the direction of the electrical force on a small positive test charge at that point, okay? So, if the field is positive and you place a positive charge in it, the field is going to point away from the charge. If the charge is negative, then the field is going to point towards that charge, okay? So that's what the picture on slide 3 represents, okay? So, since it has magnitude and a direction, it's a vector quantity. So we can use vectors to represent it, which is great. So you use, we call them field lines to represent the field. And where the lines are farther apart, the weaker the field is. So closer together, the stronger it is. Farther apart, the weaker it is. Okay? And so the picture there on slide 3 just gives you 3 examples. So that first one there, we have a little positive charge, bunch of lines going out from it. So the farther apart those lines are from each other, the weaker the field is. And then in B, we have a positive charge and a negative charge, and you can see how it looks like the field basically travels from the positive charge to the negative charge. And then on C, we have a bar of positive and a bar of negative, so it's just straight lines all the way across. And then slide 4 is some real life examples for you. It's magnets and some really fine bits of metal that are suspended in a liquid. So when you place the magnets on there, you can see the field lines. So you can kind of see how the field lines orient themselves. It's kind of cool. So electric shielding. This is kind of fun. So if the charge on a conductor, so for example, a metal surface of some kind, is not moving, then the field inside the conductor is exactly 0. Okay? So if we have a metal sphere, mutual repulsion, because like repels like, of all those electrons on the surface, basically puts them on the outside. If you were to put a positive test charge right in the middle of that sphere, it would feel no force because it is being pulled equally in every direction. Okay? Remember, the sum of the forces equals 0. And that will happen anywhere inside the sphere. Okay? Even if that conductor is not spherical, it's still going to happen. So slide 6 just gives you some picture demonstrations of that. And so that one on the top left there, metal sphere, positive test charge in the middle, it's getting pulled in every direction, so it doesn't actually feel any force on it. The top right picture there, this is what happens with static electricity. The static charge, they get distributed all over the outside of the object, and so the inside of it is technically 0. And then that bottom picture, yeah, someone sitting in a car with a giant electric bolt going through it, and they are completely fine because all of those electrons from that electric bolt distribute themselves evenly all over the surface of that metal car, so the field inside the car is 0. So, how to shield an electric field? Surround whatever you want to protect with a conducting surface. All of those charges are going to arrange themselves to make the field inside it cancel to zero. So the picture there, we call these a Faraday cage, is probably a term you have heard before. So it's named after the scientist Faraday. Basically, you can create a cage of metal and put yourself and whatever you want to protect in it. And then you are safe from an electrical charge that hits the cage, because that entire charge just goes on the outside of the cage and not on the inside. So the picture there is someone in a Faraday cage with a giant Tesla coil giving off electric sparks to it. You see these a lot at science centers and things like that. I know if you've ever been to the Michigan Science Center, they have a Tesla coil that they play with. Otherwise, if you go to YouTube and look up Tesla coils and Faraday cages, there's some examples there. I've got some, I have a couple of explanations for you, some YouTube explanations for you on that very last slide. Otherwise, if you ever saw the movie The Sorcerer's Apprentice with Nick Cage and Jay Baruchel, whatever his name was, he's a big science dork, and he makes a Tesla coil, and he stands in a Faraday cage. If I can find the clip, I'll post it for you. But in the meantime, if you have any questions, please, please, please comment on this video in Google Classroom, or shoot me an email, ekopinski@trilliumacademy.us, and I'll talk to you guys tomorrow.